Good morning, all. Welcome to the J. Irwin Miller Symposium, Is Drawing Dead? Before we start this morning, I just wanted to note a couple of things. As many of you know, in the second floor gallery, the exhibit is Massimo Scolari, The Representation of Architecture. It's an extraordinary show, and if you missed Massimo's talk on Thursday night, I know you'll be glad to see the show. In addition to that, there is an exhibition of student work in the Now Drawing Studio, which is immediately to the right as you would leave this auditorium, and then additional student work displayed around the third floor of this building. So I welcome you all to take a look at that. Those spaces will all be open through the entirety of the symposium today, so please do take advantage of that. Today's panels will occur as follows. The first panel, entitled Burning Bridges, Questioning Practice, will start immediately, followed by a lunch break. And then at 2 o'clock, the second panel will resume, entitled The Critical Act. It will be followed by a concluding address by Mario Carpo, and then a reception in the gallery. So without further ado, I wanted to introduce Turner Brooks, who's a faculty member in the school, who will introduce the panel.
Welcome back, and welcome this morning's speakers. As a lover of pyrotechnical and incendiary events, I cannot help feeling sympathetic to the title of this morning's session, Burning Bridges, as I also appreciate the tragical image of the broken pencil on the poster. But I'm actually hopeful that our 5 speakers this morning are more accurately described as bridge builders, although it sounds more corny, or even literally as makers of new pencils to connect drawing by hand back to what might be its future. For me, the driving element of a drawing is the mark on the paper. Its often complete ambiguity is a single entity until it is put together with other marks, suddenly then exploding into something that makes palpable space and has weight and atmosphere. I love to meander in the luminous spatial penumbra of a Seurat, or float through the moist, aqueous atmosphere of a William Turner, or be drawn into the depths of the crosshatchings of a Piranesi prison, there led off by some distant spiraling stair to view a far-off infinity, or to discern in Leonardo's wild spiraling pen marks deluge, steamy, metamorphosing landscapes, or to follow the subtly changing, dancing outline of an Ellsworth Kelly leaf that all of a sudden pops magically into a 3-dimensional topography, revealing a deep valley. Starting with the mark, such drawings hold the body in space, allow it to slip from moments of intimacy to those of immensity. The ambiguity between the mark and what it represents is the miracle. This is what I have not yet seen in computer renderings. My kind of obsession with the mark actually started in the only drawing course I ever took, probably in 1963 at Yale, from a disciple of Joseph Albers. We actually started drawing the word Yale, then the word Yale upside down, then the word Yale upside down and backwards, which was a tremendous struggle between the hand, the eye, and the mind. We went on to draw flower pots, finding marks to represent the New York Times printing, and then the grand climax was actually a log of wood where the idea was to find the mark for the bark. Yale was an all-male institution at this point. Some of the undergraduates got up to look into the graduate studio, longingly gazing at the voluptuous nude that was posing in there. The disciple of Albers said, "What's going on in there is sheer indulgence," and we had to go back to our bark. The drawing on the right is actually, lower right, I just put up, only done about 3 days ago by a student in a class that I'm giving on drawing, and I just like it because I think it is very much about finding the mark, and I also love its sort of ambiguity of bark. Maybe it's water, maybe it's swirling clouds, maybe it's something else. I look at a representation. The other point I want to make is about representation. There's something that has within it the power to prompt the all-important imagination to leap between itself and that which it represents. the magical power to launch the imagination into visualizing rich, subtle possibilities. The digital search for a rendered representation of the hyperreal seems wrong, and as the close proximities to this reality are only, and inevitably, I think, disturbingly surreal. Reading a representation depends on an audience with sensibility, but to extinguish that sensibility would be to promote a world where we all become pawns walking around in a creepy virtual reality. And I think it's unquestionably true that the worst buildings are those that look like their renderings. Finally, for me, the hand-drawn sketch or the crude model has the virtue of holding an entire idea or set of ideas in a state of fluid suspension from which multiple possibilities can be imagined, and from which a core sustaining idea emerges and evolves to order secondary and tertiary layers of meaning. Sometimes the clue as to the direction of evolution is discovered with a chance glance from an unsuspected angle, perhaps even a model that has crashed upside down to the floor. I don't know if Bob would agree with that analysis. I have not seen these virtues so much in digital drawings. Now on to the speakers. With Julie Dorsey and Casey Reese, the hand is being brought back into the computer's drawing process, it would seem to me. Julie is developing instruments where the gesture of drawing by hand, thinking with the pencil, interfaces directly with the screen. Casey Reese has said, "I want programming to be as immediate and fluid as drawing." Andrew Witt relates the computer as a drawing machine back to more primitive antecedents in the early 19th century, indicating that parametric design is not, after all, such a recent, sudden, apocalyptic event. The psychologist Marvin Chung is involved with the workings of the mind's cognition related to the perception of time and space. I see his work as furthering the explorations of our own Kent Bloomer in body, memory, and architecture, ultimately explaining how we can haptically navigate within the spaces of the drawings and paintings and buildings that we make. Finally, Patrick Schumacher's engagement with the parametric design as a response to infinite changing variables of desire emanating from sight, culture, and program also fit this image of the body's response to space and the increasing possibilities of the compatibility between the two. Our first speaker is Julie Dorsey, professor of computer science here at Yale. Before Yale, she was at MIT, tenured in the departments of both electrical engineering and computer sciences. She holds a degree in architecture as well. She's been developing methods of breaking down the gulf between typing into the computer and thinking with a pencil in hand. Her talk is titled, "Exploring the Middle Ground Between Sketch and Object." Julie.
Thank you, Turner, for the introduction. It's a pleasure to be here. I found yesterday's discussions and presentations to be enthralling, and I'm very much looking forward to continuing the conversation today. Digital drawing tools have evolved and now augment traditional drawing methods, letting us move ideas into the computer and develop them into three-dimensional models. But drawing remains a cognitive process that extends seeing and imagining. I contend that sketching is a medium of discovery like no other, and will describe a computer graphics system, mental canvas, which I've developed together with my students and collaborators that attempts to bridge between traditional sketching and three-dimensional modeling. We use as a starting point the traditional sketchbook drawings that architects use to experiment with various views, sections, and details. Rather than interpret or infer 3D structure from drawings, our system is designed to allow the designer to organize concept drawings in 3D and gradually fuse a series of possibly geometrically inconsistent sketches into a set of 3D strokes. Our system uses strokes and planar canvases as basic primitives, and the basic input of mode of input is traditional drawing, either on paper or on a tablet. 3D computer modeling systems have become very successful in design, and especially in architecture. In particular, CAD systems have become essential for the development of complete documentation of structures to be built. CAD models are often developed late in the design process as a tool for documentation and communication. Such models enable the precise specification of materials and their configuration and can be used both to perform both visual and performance simulations. Recently, there's been considerable interest in 3D modeling systems for the earlier phases in design. And sketching programs such as Google SketchUp that allow users to quickly define rough 3D definitions using specified gestures and commands have been developed. Many of these programs follow a simplified form of the procedure for defining a structure in a more sophisticated CAD system. Larger masses are defined by extruding building footprints, details subsequently added by defining small geometric structures on these masses and by attaching texture maps to faces of the building models. At each point in the process, the user has a well-defined 3D shape to work with, which can be viewed from arbitrary points. This approach allows a user to experiment with shape, but facilitates just one of many ways a user may want to develop a design. A classic example of a design that could not be roughed out naturally in a CAD-like system, and an inspiration for this project very close to home, is Yale's Ingalls Rink, which I walk by every morning. In looking at Saarinen's early sketches for the building, one sees concepts, ideas not yet fully formed, and loosely defined shapes. The goal of Mental Canvas is to provide the freedom to experiment with similar non-traditional and complex forms. This, to my mind, requires a different approach, focusing on how a user can organize concepts in 3D rather than on many current efforts in modeling and sketching research that attempt to interpret simple sketches as 3D shape. Architects, of course, have long used sketching as an aid to visual thinking in analysis and design. This diagram shows how seeing, imagining, and drawing interact. For example, seeing facilitates drawing, while drawing invigorates seeing. Drawing stimulates and expresses imagining, while imagining provides impetus and material for drawing. And imagination directs and filters seeing, while seeing in turn provides raw material for imagining. Visual thinking is experienced to the fullest when seeing, imagining, and drawing merge into active interplay. Now, few people possess the ability to design without drawings or other visual media. Historically, visual thinkers have clarified and developed their thinking with sketches. For example, Watson, recollecting the thinking that preceded his discovery of the double helix structure, wrote that one important idea, quote, came while I was drawing the fused rings of adenine on paper, end quote. Often, drawing and thinking are almost simultaneous, with the graphic image appearing as an organic extension of mental processes. Edward Hill, in his Language of Drawing, likens drawing to a mirror. A drawing acts, as he said, as the reflection of the visual mind. On its surface, we can probe, test, and develop the workings of our particular vision. Drawing not only helps to bring vague inner images into focus, it also provides a record of the developing idea. And drawing provides a function that memory cannot. The most brilliant designer cannot compare a number of images side by side in memory as he or she can compare a wall of tacked up sketches. I'm particularly interested in drawing's ability to extend one's thinking in contrast to drawing as a means of communicating a well-formed idea, which of course is what CAD is so good at. Here are a couple of examples. Sketches, I'm very interested in the notion of levels of abstraction that one often sees in a single drawing or a series of drawings that are assembled together, as you can see here by Louis Kahn. Here we see verbal notation, orthographic projection, and perspective to probe his thinking from varied viewpoints and levels of abstraction. And here we see the dissective capabilities of drawing, which Cami Brothers so eloquently described yesterday, where Leonardo is thinking about external surfaces and internal structure at the same time. There can be no doubt that computer modeling and fabrication allow the representation and construction of novel forms, yet they may well impede ideation in the early stages of design as they require well-defined geometry, no matter the stage of the design process. Drawing, by not requiring geometry, supports speculation, and in doing so offers an incomparable aid to visual thinking and discovery. Henry Moore's idea sketches shown here are instructive in this regard. They are concerned with the gestalt of a sculptural idea, with bold patterns of light and shadow, and with overall relationships of line, volume, and space. Abstraction allowed him to explore many ideas quickly. Moore noted that he sometimes began sketching with nothing in mind, then discovered an idea in his doodlings. As he put it, drawing is a means of finding your way about things and a way of experiencing more quickly than sculpture allows certain types of tryouts and attempts. So if drawing is so valuable, but is limited or even discouraged by CAD systems, where does that leave us? Our system aims to bring sketching back into the picture, pun intended. In the remainder of this talk, I'm going to describe the mental canvas, our system, and then demonstrate it through a series of applications in design and analysis. This slide, I think, was helpful, especially in looking at listening to talks yesterday and trying to be very precise about what one can do in different kinds of media. This describes 2D sketching versus 3D modeling. Sketching, of course, is fast, fluid, and expressive, yet it's limited to static views. 3D modeling, on the other hand, requires a precise geometric description at all times, yet it affords the ability to change views. Our system explores the space between these two representations. Simply put, you might think of what we're doing as a beginning where traditional sketching leaves off. CAD systems are designed to create well-defined 3D models and then automatically render views of them, rather than letting a user draw a view from scratch. Our work focuses on allowing the user to draw 3D shapes as an assembly of gestural strokes and to easily move, edit, and refine those strokes. The core idea driving the development of our system is to allow users to develop coherency in 3D gradually. Here we see two examples of stroke-based models developed in our system. The user begins by creating sketches in 2D and then is allowed to pull apart and position the strokes in the 2D sketches to begin to suggest a 3D form. The top sequence shows 4 sketched views of a house that are positioned relative to one another in the center, and then a new view is generated on the right. The bottom shows the development of a mixed-use complex, which was done by actually an MArch student here in the school. A 3D sketch in our system is built out of invisible planar surfaces, which we call canvases. Canvases are positioned and rotated in 3D space using the traditional CAD tools of position, rotate, and scale on the 3 coordinate axes using a tablet pen. The user can draw freely and also import sketches from paper if he or she so desires, and can set down strokes on the active canvas. Strokes can be pushed from a particular view onto another canvas, allowing drawings to be moved in space. The best way to describe this is to just show you. So here's a simple editing session where we have a canvas, one canvas in the foreground. And designer, we've sped this up, obviously, for the purpose of demonstration. If the user can just sketch with strokes, and you can do things like you can do with regular paper and erase. We can also take a canvas and move it around. So this is like you're drawing on an overhead transparency and moving it around in space. We also have some other tools that you don't have with paper. You could make certain pieces of the drawing opaque. So you can sort of turn a set of strokes into a kind of surface. Here we're now looking at several different canvases. And this shows the ability to add a new canvas. And then you can take some strokes from this active canvas in the foreground and then project them out onto another canvas in the space. This allows you, for example, to start drawing in a perspective view and then push things into an orthographic projection, if you will. But the idea here is that these canvases are just like scaffolds. They're holding strokes in space. And the form you see is a result of the overlapping of these panels or canvases. This shows the ability, all in this concept of one drawing, if you will, to show some details and also to add annotations. And up along the top, you can see what we call bookmarks, which specify some key views, and they're sort of special cameras that you can use as windows into the world. Here's just to drive this point home about the assembly of sketches and that the form emerged from the overlap of the sketches. This is a series of drawings for a kind of opera house, a variety of sketches at different scales. And then this is putting some of those drawings together inside mental canvas. So now we're sort of looking at overlapping views, and we can manipulate the transparency. So what we're really seeing here isn't a 3D model at all. It's just strokes in space. And what this allows is for us to actually look at the in-between space, what happens between views. This shows an example of some analytical drawings developed by an MArch student. Here it's a San Carlino alla Contrafontaine by Borromini, which many of you know. So here are some photographs of the courtyard. And here are a set of sketches that were drawn with our system. So they're just strokes, again, with some annotation. And now we can actually take some of these drawings and move them around. So instead of just having them as pages in a sketchbook, you can put them together. And here's another sort of live session recorded, where you can see how some of these drawings can be assembled together. And this is going inside the drawing. Again, the only representation here is just strokes on canvas. And now moving to the interior. The interior is obviously very complicated and interesting as you move from the bottom to the top, the way that the forms are arranged. And so this is a whole collection of analytical drawings that were done of the interior. with lots of different views and different components and different ways of breaking the drawings apart. And here again is a live view of the drawing or model, if you will, inside mental canvas. It says kind of as, almost like you could go inside your sketchbook and move around. And this shows the kind of dissective ability of even within a drawing that you can start to pull things apart. And this is an interesting one. This is a perspective drawing on a single canvas. And then, so first you'll see the canvas, it's just a single plane. And then after it's been pushed out into a series of additional canvases. And you can see that the perspective doesn't quite work. And here we see an example of a design process, project that was done in the system. It was a mixed-use complex with 2 towers. And here you can see early stages of the design process, quick sketches. And then a designer took one of the 2 towers and took it, developed it further. Again, now sketching in some opacity and adding more detail. Again, this is just a bunch of strokes in space. So, so far what I've shown is sketching pretty much devoid of any sort of context. And of course, architecture is all about design in spatial context. So one of the things that we've been exploring recently is how can we provide some context for sketching that is lightweight and amenable to the kind of sketching that mental canvas affords. So there are a variety of different kinds of representations available. One is panoramas, which are very helpful in giving a broad view of a context, but they're not so useful at a certain point because they only have a single viewpoint and they don't offer any sort of occlusions, and that's very important in a variety of different kinds of spatial contexts. At the other end of the spectrum, we could look at full 3D models. They're way too detailed and often extremely difficult to acquire, so often also not particularly suitable for providing context for sketching. So in very recent work, we've been looking at how we can represent designs in context. And this example, Frank Lloyd Wright's Kaufman House is a kind of example that's very, very challenging because here, of course, you have both the built structure and the landscape are embedded. So recently, we've been trying to look at ways that we might provide a kind of lightweight context. So here's an example of real video taken of a rural site. And the question we're interested in is how can we represent a complex setting like this in a form that's amenable to conceptual design? We've been working recently on something called in situ, which is a kind of extension of mental canvas, which is intended to provide such a lightweight representation for sketching. So in situ leverages the availability of data about sites from things like Google Maps and Bing Maps, as well as elevation and aerial photos and simple site measurements and photographs. So the idea is that we can take these photographs taken with a digital camera, variety of site data that's available and some basic site plan measurements, and combine that into a kind of backdrop that can be used for sketching. Here's an overview of how all the pieces here go together. We take these input, various types of site surveys, photos, and so on, import them into our system, and first we create a kind of aerial, from the aerial map and elevation data, we create a kind of a height field or a canvas that has height that represents terrain. And this can be combined with aerial photographs. On the left here, you can see one of these height field meshes and then the terrain with the aerial photo applied. And one of the things that if you go out and take a lot of pictures of a site, what's important for being able to use such a representation for sketching is that you need to know where you are. So we use a simple set of measurements, something like 8 stakes in a complicated site, to provide a kind of scaffold to hang pictures. And we also make use of basic GPS measurements. And from that, we can figure out where we are on the site and hang photos, if you will, and structure the site so that it can be used for sketching. This just shows the ability to take a few measurements, combine them together, and figure out where cameras are. And eventually, we can create some kind of 2.5D representations that we can use underneath our sketching system. So one of the things we do is we import bundles of photographs. So you could take hundreds of images of a site and then have them all kind of registered, if you will, within the context that you're creating. And also organize them in a way that it becomes simple to navigate. We also have some interactive tools so that you can create linked pop-ups. So you could start out with a photograph like this. We can automatically, with minor, sort of modest user intervention, estimate where the camera was that took the photograph. We can go in and block out some part of it as a pop-up, and then generate a canvas in space where the pop-up should be located. And this is an example of this is a site that we're working with a sculptor on. She's designing a large sculpture for the new section of the High Line. So this is how the lightweight context comes together. So here's the imported elevation data. Again, this is available for just about any site. And then we apply the aerial map. And then this is importing point clouds. So if you've taken a whole bunch of photographs of the site, these are now localized. And then you can go in and create pop-ups. And this is an interactive process because with any site, a designer often has particular features he or she finds important. And so we have the ability to go in and pull those out. So this is, we start out with a real site, and now this is the virtual site. And I should say that this can be represented with either photographs or with strokes or some sort of representation in between that might be more painterly, for example. And then the interesting part begins. Here you can actually sketch within this lightweight representation. So we've sped this up again just for illustrative purposes. So the designer is sketching a house in the woods. And note that, again, the basic representation is just strokes. So we're creating a canvas, but you can also manipulate the backdrop here. And I show this to show you that this representation is actually in, these sketches are positioned in the site. So up along the top here, you're seeing a series of bookmark views. And then all of the drawings that you make are registered, if you will, with the rest of the site. And on the lower right here, you can see a bunch of different kind of camera angles. And this shows that what I mentioned earlier about with a panorama, you don't have occlusions. And so this shows you can see here you can bring in trees and other features on the site and sketch around them or behind and so on. And this is another example. This is also a house design, and this is without the pop-ups. This is just using strokes. And I show this just to give you an idea of what it's like. This is just a series of sketches, again, put together. So we can move around and look at particular views, but note that this is actually incomplete. If as we move around, you'll see that this house is in pieces. It's not yet fully formed. Our current interface is a Cintiq tablet display system, which is a lot like your iPhone or iPad. So we're moving toward making something that's really compact and portable so that you can use it like a sketch pad and have digital camera, basic GPS, and all that all in one single device. In many ways, the system that I've presented today is like a sketch in that it's a work in progress. And it's, in that sense, it suggests, I think, as many new directions as problems we've solved to date. So many things that we're looking at right now, one is different kinds of rendering styles, lighting effects, atmospheric effects, and shading. And we're also working on incorporating a temporal dimension to the system. And the context that I showed you, although we're able to create these pop-ups that you can use to sketch, we're also interested in, like as in the Kaufman house, being able to actually edit that context. So be able to manipulate terrain and vegetation to look at the interplay of built form and landscape. And another interesting direction which we've not explored yet, but I think could be neat, is to create physical pop-ups out of the system. This could even be done just on a laser printer. And Capability Brown often presented his landscape designs as pop-ups. So in addition to, I hope, sort of elevating sketching again, perhaps our work could also start to push more toward elevating pop-ups as a way of presenting and studying designs. So I just want to end by acknowledging some of my collaborators and students, and particularly Patrick Paskowski, who's the lead developer on the system, who's a PhD student, and also Andreas Pakalci, who's finishing his MED thesis, and who just learned how to use the system in the past couple of weeks and has made a number of the examples that I showed today and has provided lots of insights. Thank you very much.
Thank you, Julie. Great. Second speaker is Andrew Witt. Andrew Witt is based in Los Angeles as Director of Research at Gary Technologies. He's also a member of the architectural faculty at Harvard. He has degrees in both mathematics and architecture. His talk, A Reverse History of Mechanized Drawing, 2012 to 1900.
So first, I, of course, would like to thank Dean Stern, Victor, and George for the invitation to present, as well as the inspiring and impressive presentations that we've seen throughout the conference so far. I'd like to begin as a point of departure with Antoine Picon's observation yesterday. The drawing, historically, has played a spectrum of roles within design, of which the design sketch, or partie, is but one. If the discussion up to this point has, to some extent, been dominated by the primacy of the design sketch, I'll take a somewhat different section through the topic. In particular, remarkable innovations are occurring in our ability to make things, and the way designs are best represented in order to be made. The documents that describe such processes could historically be called measured drawings or construction drawings. Indeed, these drawings are the currency of architecture, quite literally because they're how architects legally monetize their labor, and thus play a key role in the professional self-understanding of the architect. The measured drawing has a history that's somewhat distinct from the sketch or partie, emerging as it does from the legacy of engineered drawing. In one sense, with this lecture, I'll try to go back to the future to suggest how the influences that shaped the development of engineered drawing, mathematical visualization, mechanical experimentation, tacitly continue to influence the development of digitally enabled design today, in particular, the sort of parametric turn. In another sense, it proposes a reconsideration of the relationship between drawing and model. 3D digital models are increasingly replacing drawings as a key element of project communication and construction. And that situation, to some extent, is a return to an ancient state of affairs. After all, during the construction of the Florence Duomo, it was the model that the craftsmen swore allegiance to, not a set of drawings. In a sense, some years after that moment, the drawing might itself be considered an upstart form of representation. A poor substitute for the model, lacking spatial clarity, structural analogy, immersive quality, even material specificity. Design models, digital models, recapture many of these advantages and in a more versatile way than their physical counterparts. Yet architects maintain an ambivalent, if not conflicted, view of technology in general and the computer in particular. The heroic view of architecture as an autonomous and unmediated manifestation of the will of the architect still holds public and private fascination. Even technical innovators may duly defer to this self-characterization of architecture and are often at pains to characterize their work as design as opposed to engineering, which has become a pejorative term. The advent of a technology that's so powerful, fast, automatic, perhaps even intelligent, presents a subversive confrontation to the architect's sufficient and autonomous will or knowledge. The perceived association of the computer with striking formalism and tentative material resolution makes it only more suspicious to the traditional understanding of design. So we'll try the arrows here. My interest in technical drawing and the mechanical instrumentation that enables it was catalyzed by an improbable find in one of the storage cabinets at Gary Technologies. This device, the device pictured here is a planimeter used to calculate and measure irregular areas, normally on maps, but also on irregular shapes in design drawings. It functions by fixing a point, tracing the other one along the length of a closed curve back to the original starting point. In fact, it's a mechanical encapsulation of a mathematical proposition called Green's theorem. It's a physical way to calculate integrals. From the 19th century to mid-20th century, they were used commonly in engineering graphics, but are almost unknown today. Finding one was a little bit like finding somebody wandering in the Sahara. Is very surprising on many levels. And it seems to me a sort of clue of the unspoken geometric and mechanical history of the office, a parallel history to architecture itself of mechanized drawing. So the digital revolution of the last 20 years, and in particular the latest incarnation of parametric design and deliberate intervention in CNC processes, has helped create a remarkable series of innovative projects. In short, it's enabled building that would have once seemed unbuildable. Here's but one example, Asymptote's Yaz Island Hotel, which suspends above it a constantly varying, self-supporting grid shell of custom-fitted glass components. Such examples, of course, could be multiplied. They've become so numerous that we can easily forget how miraculous they seemed only 15 years ago. In principle, the design sketch for many of these projects may have been done at any time in the past, but the capacity to achieve them in built form lies uniquely in the present. New means of representing design intent have also allowed the synthetic integration and embedding of design intelligence, not only of the architect, but also of engineers, consultants, builders, into a shared adaptive database. In short, the drawing has been transformed from projective markings into a database of responsive process intelligence and blurred the boundaries of authorship in built work. The seriality of classical design process gives way now to concurrency and simultaneity. The building, in a way, has become a kind of wiki. The radically extended capacity of the model over the drawing also facilitates the efficient use of material processes which would otherwise be impossible because of the specificity of their design requirements. Wood forming, glass molding, parametric metal stamping, and of course now robotic assembly require high fidelity and machine-readable representations of the building in order to function. This is only possible with a 3D database, which is inherently multi-representational. The development of multi-representational and constraint-based models demonstrates that the computer is not, in fact, a frictionless and effortless medium. Far from it. In fact, it facilitates an intentional embedding of resistance through logical rules and programmed responses in a way that allows designers to foreground design and still be confident of constructability. In such systems, the architect does not only design a project, but also a metasystem in which the project exists and is capable of being realized. In this sense, architectural authorship is actually radically extended. Compared to this, in a way, the paper drawing itself feels frictionless and free of constraint. New models embed not only static material logic, but dynamic assembly descriptions as well. They are methodological armatures as much as design tools, frameworks for the orchestration of labor and time. Many of the contemporary projects share sort of conceptual hallmarks that are characteristic capacities of digital design. These capacities are not at all new, but in fact have deep antecedents, even perhaps precedents, in machine experimentalism and the culture of engineering representation, with which technical drawing and architecture shares a lineage. Three particular formal conceits are recurring threads throughout this history. First, combinatorial permutation, or the continuous evolutionary variation of specific module elements. Differential cartography, or the mapping of subtle quantitative facts or constraints across a space or surface. And swarm logic, which is actually the connection of permutation and cartography. That is the use of informatic maps to drive differentiation across an assembly. Contemporary process is characterized by mass production of customized details, and it's through this swarm logic that drawings become maps and deformations of these details. In fact, sophisticated 3D models have also multiplied the modes in which drawings are used, perhaps even extending the spectrum of technical activities connected with drawing. Facade maps, model-generated fabrication drawings, representations of 3D survey data, all these actually extend the vocabulary of what a drawing can and should do. In short, the short disciplinary memory of architecture with respect to technical matters obscures the degree to which the technical, procedural, mathematical, automatic generation of representations, indeed parametric processes, have informed the culture of design and drawing for at least the last 2 centuries. In fact, I would argue that the professionalization of design is deeply connected with the emergence of technical drawing as a discipline, and in turn with the mechanization of drawing. The current debates on the heritage of drawing could be reframed by demonstrating this long-standing connection between measured drawing and mechanization, and trace the material antecedents of our own visual and methodological fascinations. So why machines in particular? So ambitious form making of the type that I've sort of described and shown requires a virtuosic mastery of certain spatial geometries. It's a specific type of design knowledge that's somewhat specialized and difficult to deploy. Machines, including computers, actually provide a way to encapsulate this knowledge in a more usable and repeatable way. Of course, such machines raise certain epistemic challenges. They abstract systems and detach the user from their operative logic, arguably requiring more instrumental and less design knowledge from the user. But they also offer the capacity for an enduring knowledge culture, distinct from the perpetual revolutions of ideology. Stitching together the separate epistemic archipelagos that litter the history of calculated drawing can reveal a consistency with which parametric themes have emerged out of mechanical control. And indeed, parametric practice carries on a certain project of geometric control through variation through, in its many guises, has been apparent in architecture almost continuously since the early 19th century. So beginning from the recent past, this presentation will reconstruct a history, or maybe more modestly a chronology, of procedural and electromechanical drawing devices, and build a narrative of the recurring techniques in this machine culture of design, which is continuous with our own preoccupations. Many of these moments, like digital practice itself, until recently fall at the margins of architecture. The various moments in this reverse chronological sequence, design computation, design science, mechanical combinatorics, projective and stereotomic geometry, the cartography of curvature, propose a historical framework for the current debate on the role and impact of computational methods of representation. Of course, we'll begin with Bilbao, one of the earliest progenitors of this type, and one of the first to employ computer drawings to verify constructability on a large scale. Associated with the model was a series of overlaid simultaneous analyses with specific and distinct meaning. These maps made the model functionally polyvalent. The Bilbao process itself was a direct response to the limitations of classical drawing methods, which could only be overcome through a digital multi-representational database. Here we see one of the last projects in the office to be done totally through process of projective geometry. The catalyst for the digital methods was in part the limitations of descriptive geometry in the precise describing of complex shapes. The complete development of such methods was taken to its limit on the Weizmann Museum, where each conical surface was developed in painstaking detail. The labor was enormous, and this gap in control created the need for digital methods. Of course, the cartography of complex surface geometry had been a theme occupying design for at least 20 years prior. And the use of projective geometry in the measured development of construction drawings itself has a precedent in Buckminster Fuller's work. Fuller, in particular, developed drawing methods specifically for the mass customization of his dome structures. And the construction drawings for the domes themselves attest to the variation required in real terms to achieve a presumably simple structure. Field-like yet strongly figural, Fuller's mesh has become a deductive and integrally unified solution to a simple question of enclosing space in the most efficient means. They create a compact and sewn-up world. The geodesic method of discretization was profoundly complex in practice, a cartographic operation in its own right. Strangely, Fuller did not use computers himself to calculate the angular values and instead used the drawings as heuristic tools. But Ron Resch, a contemporary of Fuller, was one of the first to use digital computers, to my knowledge, in a generative way, akin to what we might call parametric today. He used them to calculate the discretization drawings of space frames supporting geodesic domes and engage problems of mapping dynamic geometry. In his 1973 paper, the topological design of sculptural and architectural systems, he details what sounds suspiciously like a manifesto for parametrically enabled digital fabrication. Quote, "I will show how the conception and fabrication of designed objects have a topological and geometric aspect. Currently, these objects may be characterized as emphasizing the geometric aspect by limiting an entire class of objects to be a unique one. Finally, I will show the introduction of the computer into the design and production process makes possible the topological aspect, so that the automation of custom-made objects might replace a series of identical ready-mades. So that was in 1973. In fact, in the 1970s, Resch undertook a series of computer-controlled fabrication experiments of tessellated domes through to completion, thereby becoming one of the first examples of constraint-based automated design to fabrication. Resch's armature is the triangular mesh. It's a representation of a curved surface. And plays a particular role in architecture's recent fascination with surface geometry. This fascination has made landscapes out of spaces and spaces into landscapes. The articulated free-form surface of contemporary projects have all the complexity of geospatial terrain. Each inflection and each fold must be planned, designed, analyzed, controlled. These surfaces accumulate whole sets of unique cartographies, maps of curvature, material stresses, environmental performance. Such surfaces compose increasingly field-like spaces. Deformation is a watchword, but so is control, a precise and constant interaction of design and engineering in the service of determined effect. So this is Resch's film, the content of which is from around 1963. In the film, we see a series of physical models that guided Resch's thinking. All the paper physical models are composed of one continuous sheet. Let's see, and then finally we'll see his digital simulation. So even here, there's actually a tactility to the model as well in the process actually of going through and creating these prototypes. I imagine there was some kinesthetic memory being developed there as well. So here we see the process which he went through to generate his simulations. There was no such thing as a screen. So in fact, plotters were used to create keyframes. And then these simulations were created. What's interesting about these simulations is the fact, of course, that they're dynamic, that they have specific structural logic and kinetic logic. And so in a way, he simulates the material properties of folding in the computer, in which for 1963 and for all the labor involved in all those plots, I have to think is something respectable. So here he even disaggregates the dome, pulling the pieces apart to reveal the unique maps of the two layers. So others took geometry as central to the digital process. From the early 1960s, the Laboratory for Computer Graphics and Spatial Analysis at Harvard GSD held a special position at this particular intersection of geometry and design. Funded in part by the Department of the Navy, which is kind of fascinating because when you look at their documents, they look like declassified intelligence reports or something. Funded in part by the Department of Navy and known as the birthplace of geographic information systems, the actual mission of the 40-person lab was much broader and encompassed what might be called theoretical geography. That is, the general study of the topological and geometric properties of surfaces and spaces. The lab actually took on as a project the abstract cartography of surfaces, studying topics ranging from triangulated irregular meshes to four-dimensional descriptive geometry. They engaged problems of the topology of connectivity and the implications of form and space. These experiments were a sort of visual manifestation of the wider fascination of control theory and feedback processes during this time, the mid-50s. It was only slightly after the first patents had been filed for computer-controlled machining equipment, including the patent drawings here for the first CNC routing machines. The engagement with material form, its resistance to the requirements of fabrication, was ground for fertile research during this time. In particular, the same devices that were used by Resch to draw and plot could be retrofitted to carve material. And of course, artists took on that project. Artists began to appropriate these machines to create design forms. Of course, the original form itself had to be drawn mathematically, but thereafter, the tool itself would draw in space or carve, as we just heard yesterday. So Charles Schury was among the pioneers of this new type of sculpture. So this is a sculpture of his from I think it's also from '63, appropriating the machine to draw material topographies. And one of the things that I find remarkable about this is the sort of prescience of Surrey's approach. I think we're more familiar with some of the work of, say, Bernard Cash on the left, but Surrey is sort of right in that idiom. Of course, architects were also fascinated by computer-controlled machining and indeed created proposals for machines to form material. Here we see a proposal by Renzo Piano for a dynamic electromechanical mold machine, roughly contemporary with Surrey's work. So it's kind of, I don't know, this is kind of a fascinating discovery for me that Piano actually would have made these projections around machine articulation of fabrication. So Resch's work with digital computers followed the cinematic experiments of others with analog computers, and a number of experiments with oscillating wave machines to simulate certain deep spaces through overlapping line work and periodic Lissajous curves. One of these is, Desmond Paul Henry and Heinrich Heidersberger are specific examples. So World War II, World War II brought a new generation of digital and analog electronic calculating machines to the fore, including ballistics computers used for measuring the trajectories of missiles. So Desmond Paul Henry created quasi-periodic curve drawings with an Army surplus bomb sight computer. So he essentially adapted this computer, which was intended to work in real time, charting the courses of ballistics, and instead applied it to drawing. So he described these sort of results as densely packed helices subject to various degrees of distortion, both intrinsically and extrinsically. Extrapolation of the spatial implications of mechanized drawing, extrapolating those implications, Henry linked his drawings to Darcy Thompson's formal analysis of spicules, cells, and cellular aggregations, intending his machines to simulate the evolution of these types of biomorphic and mathematical structures. Speculations, if you will, in the evolutionary biology of drawing. And I wanted to point out also that the left drawing has a ground plane. And so maybe there's an architectural intention, I'm not quite sure. Beginning in 1955, Heinrich Heidersberger, who was an architectural photographer, undertook the construction of simpler but more spatial devices, which traced the oscillation vibration of a light beam on photographic plates. Heidersberger created several distinct iterations of the machine, the most sophisticated covering over 20 meters. So there's him kind of immersed in the machine. The product of this machine was a series of rhythmograms, luminous images of permuted curvatures. These rhythmograms had deliberately spatial properties, engaging a relativistic sense of space and time, capturing something of the cinematic and combinatorial possibilities of machine drawing. It's not incidental that these drawings leverage what we would now call the wireframe. In the wireframe, a prototypical digital representation, we have a pure oscillation of inside and out. It was a key mode of spatial experiment in the early 20th century, taken up, for example, by Albers in his drawings of structural constellations. But it also claimed a scientific connection to the early 20th century emergence of new types of mathematics. It suggested a way not only to represent four-dimensional space. So on the lower left-hand corner, you can see a mathematician's drawing of the four-dimensional hypercube, and then Van Doesburg's own hypercubic house, which he hoped to represent that spatial, where he hoped to leverage that spatial complexity, I guess. It also suggested a way to represent, the wireframe also suggested a way to represent deep experiential, perspectival three-dimensional space in a single plane. The question of mathematical measurement in particular, and the distortions and inversions possible in a mathematically measured space had set the stage. One of the most ambitious of these machines was William Rigg's 1927 device for combinatorial curve drawing. Through the permutation of gears of various sizes, periods, and configurations, you could construct a whole range of curves, cycloids, harmonic curves. Rigg spent over a decade perfecting his machine, and it had a range of about 7 billion distinct curves, to be exact. Well, sorry, to be exact, it's 7,600,000. Anyway, it's a lot. Okay. But I admire that he calculated it to a couple of decimal places. So the machine thus became an empirical means of exploring an almost unlimited space of parametric permutations. In this particularly suggestive diagram on the lower half, published alongside his other research, he shows a matrix of curve families and their continuous parametric intertransformation that emphasizes, in fact, the stereoscopic effects of his machines. This matrix represents a combinatorial exploration, and the matrix itself, I think, is still a very valid and compelling way to represent sort of combinatorial span, as evidenced by the seminal work of Greglin's embryologic house. The Rose engine, a parametric tool for the cyclic cutting of wood, is another example, popular in the late 19th and early 20th century, all but vanished today. And what was fascinating about these types of devices is that they engendered their own type of literature, which was, in fact, a literature documenting all of the combinatorial range of those machines. So here we have the numeric representation of all the possible states, and the graphic representation of those states. And in fact, these are only one of an entire genus of combinatorial machines, each generating a curve, many with specific architectural implications. So one of the things that we find in the 19th century is architects actually specifying the types of machines that they need in order to create specific types of drawing, as sort of prototypical hardware hacking, if you will. In fact, it was the syntactic project in architecture that catalyzed this machine invention. The volute and architectural compasses became the mechanical embodiment of an intellectual project for the rational unification of the orders. This mechanical unification has its more distant antecedents in the formal rationalization of Claude Perrault. The fundamental transposition of the rationalization of the orders from a historical problem to an abstract, formal mathematical problem made possible the connection of mathematics and mechanism to the ideological and historical problems of architecture. In the meantime, the new geometric methods of projective geometry created a more urgent requirement for tools that could encapsulate complex geometric operations rapidly, almost algorithmically, and assist designers in the generation of projections and intersections. The construction of conic sections, such as ellipses, parabolas, hyperbolas, was particularly key because these were frequently occurring sections in projective construction. Some of the most sophisticated instruments addressed design problems from antiquity. So the precise proportions and curves that describe the profile of the classical orders, for example, were a matter of rigorous and laborious calculation prior to the advent of such machines. And as I mentioned, projective methods as well, particularly the calculation of vault intersections, benefited from specific machinery. In fact, such machines became standard enough that in some technical treatises, they began to be recommended as a way to construct those intersections. Of course, the machine culture of design included not only drawing machines, but modeling machines as well. Kinetic models which were used to generate their sophisticated intersections. So in this case, along the top of this model, there's a rail which you can position the two sort of floating circles, and as you reposition them, the intersection in between is sort of physically recalculated. And here we see an example of the types of machines that were developed during this period of time in Europe. So at the top is actually an excerpt from a treatise by Giambattista Soardi from the 18th century. For some reason, in the 18th century, Italy was a very fertile place for the development of these types of drawing machines. So his prototypes became an inspiration for many later ones. The lower left-hand corner was a model actually designed by an architect for specific use in architectural applications. And then there's a physical realization of Soardi's prototypical model. Just as in the 20th century, numbers became a means to calculate curves, in the 19th century, the reverse was true, that curves were used to calculate numbers. The porosity between drafting and scientific instrumentation and their interdependence in cycles of innovation is exemplified by Joseph Clement, a well-known draftsman and one of the foremost makers of precision instruments in 19th century Britain. Clement won national recognition for the design of architectural drawing instruments, particularly those for the construction of ellipses, and worked extensively in the manufacture of automatic machine tools. But his most remarkable collaboration was in the construction of Charles Babbage's difference engine, the first large-scale mechanical computation device between about 1824 and 1833. As the principal engineer behind the execution, Clement drafted and planned the interworkings of hundreds of interdependent gears. Babbage's project to create a machine for the automatic mechanical calculation of mathematical tables marks the most ambitious and systematic attempt at automatic computation up to that point. And it prefigures in many ways the digital computers of today. And it's remarkable, I think, that at the center of the project was a draftsman who was intimately involved in the creation of drawing machines specifically for complex architectural work. Of course, sophisticated geometric calculations of exuberant form had made such instruments necessary, particularly for fabrication. Here we see the complex operations necessary simply to unroll the stringers of a staircase in an assembly. So this is the sort of developed edge of that staircase on the right. In fact, there was a substantial subliterature purely on the drawings necessary for projective development of topologically sophisticated staircases, which attests to the almost parametric control of variational geometry that was necessary to achieve 19th century formal ambitions. So if projective geometry was an intensive mode of measured drawing, meshwork triangulation became an extensive mode, mapping terrain for a range of operational transactions. So on the left, you can see a triangulation of India around 1850, and on the right, the triangulation of Long Island, which dates from slightly later. Here, this is a triangulation of the Himalayas undertaken as that area was surveyed. Actually, it was the expedition that named Mount Everest. And you can see in across the bottom the sort of unrolled geometry, actually, of the Himalayas. This is about 1850. Through these triangulations, surveyors and planners mapped the complex surface of the Earth itself in a purely abstract network of mutually coordinated perspective projections. Locally relative and multifocal, the detailed resolution of this framework was constrained only by quantitative requirements. These geodetic methods expanded the already deep connection between cartography and geometry, and the understanding of landscape became a mathematical endeavor. So finally, we arrive at the early 19th century and the two essential systems of technical drawing that formed a key part of engineering curricula in which many architects were trained. On the one hand, we have descriptive geometry, a framework of local control of complex surface geometry. So here you can see this is an excerpt from Monge's descriptive geometry, which shows his development of certain tangent surfaces. On the other hand, we have performative cartography, which emerged from military engineering. More operative and generative than surveying, the design of fortifications was dictated by siegecraft stratagems and ballistics calculations. Its geometry was not only planimetric, but sectional as well, drawing on the parabolic profiles of ballistics in order to calculate the proper elevation and ramp conditions for the fortifications. By translating the parameters of this control, angles of wall declination, trajectories of combat engagement, and radii of ballistic ranges into a mathematical system, the problem of state power was radicalized into a geometric formula. In these two systems, one for local representation, the other for global, we find something of an ancestry for the contemporary project of cartographic parametric design. So the trajectories woven through this chronology are in full evidence in the work and debate of digital practitioners today. The divergent and conflicting approaches of these practitioners, I think, conceal a common conviction, however tacit, that the computer has radically expanded the scope of the possible in architecture. Yet with this new possibility comes fundamental questions about autonomy and authorship. Autonomy implies a sort of independence of the syntactic and rational systems of architecture from the extrinsic technical or ideological constraints. It also affirms the role of the architect's will, whose syntactic choices in turn sustain the autonomy project. This truly autonomous act of will implies a sort of epistemic self-sufficiency. The designer has a specific knowledge to create form, and instruments that could imply that the designer's knowledge or capacity is incomplete call into doubt this heroic view of architecture and authorship. Thus, the disciplinary implications of the computer hinge on questions of knowledge. Does the computer as an intelligent tool enhance or diminish the capacity of the architect? Can the computer or software encapsulate knowledge? If yes, can a user be said to know a process that is abstracted, encapsulated, and automated in a machine? Do machines in and of themselves represent a sort of latent knowledge? Perhaps, and hopefully, these questions will be best answered by the future history of architecture's new medium. Thank you very much.
Thank you, Andrew. Our next speaker is Patrick Schumacher, who has a background in philosophy and architecture, studied in Bonn, London, and Stuttgart, started working with Zaha Hadid in 1988. His talk is titled Medium and Form, the Drawing Within the Autopoiesis of Architecture, and relates to the title of his recently published book, The Autopoiesis of Architecture. Volume 1 has come out, and I think Volume 2 is coming out in the spring.
Make sure everything works.
Yeah. Can bring that up? Okay. Good morning. Wow, this was a very, very fascinating talk. Thanks a lot. Very insightful and for me, a lot of new, interesting aspects of the history I'm kind of working within, but didn't know I was working with it. My talk today is delivering a series of distinctions which cross the divide between traditional drawing and contemporary digital modeling and parametric modeling and scripting under the notion of architecture's medium. And the design medium as a universe of possibilities, which I feel has massively expanded, obviously, through the incorporation of the new digital design tools. Oh, this wasn't fixed. I will not say much, but these are the kind of phrases or notions which came to mind when I was listening to yesterday's debates. 3 on the side of relating to the hand and the other 3 relating to the computer. To be clear, my understanding is that drawing is that in the sense of elaborated hand drawings and traditional drawings, but the freehand sketching is still continuing. But I think the concept or the category of freehand sketching needs to be elaborated. There's many different types, different functions. For instance, there is a distinction between the replete and the attenuated. It's quite a different matter whether a sketch is just indicating a series of topological relations like an organizational diagram, where most of the specific aspects, characteristics, and formal aspects of the sketch are relevant and to be abstracted from, versus a sketch which is teasing out a formal composition, some formal characteristics, stylistic elements and aspects, where every aspect and feature and moment of the drawing is to be paid attention to and carried forth from drawing to drawing into the final project. Like, for instance, some of the sketches which Saadid has been doing. So there's a big kind of range, depending at what stage in the design process and with what function, with what aspect of final architecture the sketch is contributing to. And I think there is different modes of reference to be distinguished: denotation, exemplification, and expression, which are operating in this domain of sketch-wise representation. And these two sets of distinction I'm taking from Nelson Goodman's reflections on notational systems and in his book, The Languages of Art. I just want to flick through some of the work we've been able to create on the back of the new digital design tools which I'm promoting, and which would not have been possible, as was pointed out earlier, with the traditional tool set. So there needs to be celebrated as a new universe of possibilities, of elaboration of design and construction, but it's also already on the elaboration of desires and designs, the build-up of much more intricate and rich complexity in the design, independent of the question of constructability, is already evident with the new kind of sets of tools. So I think there is a thoroughly humanizing set of tools rather than dehumanizing. And I think also, if you look back, I've grown up in a period where we had to spend hours and hours trying to build up drawings and waste our time and break our backs. That was, in retrospect, rather dehumanizing, and we're exhilarated about the new kind of freedom and light-footedness and versatility of building up designs. The reflection on the design medium is in fact come about, I think, through the challenge of what have been taken for granted standard sets of drafting and designing, that expansion through the digital possibilities, and for the first time delivering choice of medium, and therefore posing the question of the medium as something not to be taken for granted. I think that has spurned a very, very interesting discourse on the medium, and in my writings I have, in each of the 2 volumes, there is a major part dedicated in part 1 to the medium and part 2 to the design process, in volume 2 to the design process, reflecting that. And I'm proposing, for instance, just picking out one of the theses of volume 1. Architecture depends upon its medium, the drawing, or digital model now, in the same way that the economy depends on money and politics depends on power. It sustains a new plane of communication that depends upon the credibility of the medium and remains inherently vulnerable to inflationary tendencies. I will elaborate on this in a bit. First of all, in the most general terms, the medium is any reservoir of loosely coupled elements that allows for the formation of forms as strict couplings of elements selected from within the medium. For instance, the sentences are forms or strict couplings of word formed in the medium of language, understood as a reservoir of loosely coupled words or vocabulary. And in the same way, the drawn or modeled architectural forms are strict couplings from graphic geometric elements or primitives selected from the medium of the drawing a digital model. And now these mediums proliferate, and the question is with what primitives and sets of rules of creating strict couplings are we actually engaging the world of design. So the limits of the chosen design medium's representational capacity, and I would also say imaginative and constructive capacity, determine the limits of possible design speculation, and thus the limits of architecture's purview, scope, and domain of competency ultimately. Which aspects can we draw in to the kind of design universe, the design world through which we operate, think, and project forward. So this insight obviously parallels the linguistic turn in philosophy, where we realize that we can only think what we have the language for, and that is a given kind of medium we inherit and develop only very slowly. And as I said earlier, that we are now in a position for the first time to select a medium and actually also develop new media, and architects have been involved in this over a number of decades, And it has inspired architectural thinking and reflection, for instance, like in Mitchell's The Logic of Architecture, which is a treatise of understanding the constitution of design through design worlds, and it has also been an inspiration to the development of CAD systems, which architects are kind of in interaction with, and we, for instance, are collaborating with Autodesk on many levels. So I'm just offering a number of further distinctions which are important to reflect the question of the design medium. First of all, in terms of the medium, there's the design medium, which is to facilitate creative problem solving by the sequential build of complexity, the actually working medium, perhaps most important and primary for us. But there's also the medium is what I call a specialized success medium, because it functions to facilitate successful communication to outside stakeholders. And that is extremely important, because only if there is that capacity to explain and bring stakeholders on board are we actually able and even dare to communicate beyond, let's say, what conventional solutions. So we need to distinguish the medium in its various functions in, on the one hand, constructing the architect's project, which for me is that kind of design development medium, but there's also the client's project, the engineer's project, and the contractor's project to be looked at. And I think these are quite different domains and of operation of what we shouldn't lump together as simply the model or the set of drawings traditionally. And the architect's project itself is, I would argue, divided into an organizational project, which is, Antoine mentioned earlier, the kind of operates on a very abstract level with maybe a part of non-human perspective, kind of bird's eye view, or more abstract organizational relations. On the one hand, on the other hand, it's we need to at the same time always reflect that spaces and architecture organizes social communication for not only bodies spaced out physically in space through distance and physical separation, but is operating for a sentient, socialized being. We rely on perceiving and navigating and reading their spaces, so we have the project of articulation, which is to do with the experiential aspects of design and trying to simulate these aspects and the appearance and experiential tractability of environments through the design medium as well. And that's a separate project to a large extent, one building upon the other, and makes different demands and calls upon different aspects of the overall panoply of design media, which by now is to be argued in the plural sense. So, and I'm just looking at these two strands, designing the organizational project and the articulation project, and how each of them moves through a series of stages and building up complexity and determinateness through kind of successive layers and stages, which sometimes take, and often now take, up to a year or longer, sometimes 2 years. So there is this kind of drawn-out cumulative process of drawings out of drawings, or elaborating models upon models into clusters of models. But these are two parallel strands, and in the end, somehow they both feed into the comprehensive, detailed 3D parametric model, which then spins, on the one hand, the photorealistic renderings with all the lights, materials, reflections, and the phenomenology of space, and on the other hand, the more detailed files which allow us to control the detailed organization and technicalities and objective aspects of the built environment. So these are two strands which are tied together and initially run in parallel, but we need to remember that a drawing or a particular model, a particular extract of a model, because we're no longer doing drawings, a drawing is a kind of viewport. The two-dimensional plans and sections still exist, but only as viewports or extractions from these integrated 3D parametric models. But each item and also the model is often a kind of cluster of models worked on in parallel by different designers, but also accumulating and moving through time. So we have networks of drawings, and the meaning of each of them is depending on its position within that matrix, which has two dimensions, either the coordination of many multiple fragments, if you like, which together build up the kind of systematic global representation of the project, and the kind of continuous succession. How this is a kind of evolving process which evolves over a whole year or longer, with sometimes very, very large groups of people, over 100 people. And so each of these drawings or models is just a transitory fragment within that cross-referenced set of drawings processed through time, and that we need to remember to avoid this kind of fetishistic metaphysics of presence, which sometimes overcomes us when we just stare at a particular fragment, transitory fragment of these kind of larger processes. So we need to remember the difference effect in Derrida's term, also what you might call the paradox of the hermeneutic circle, that the meaning of each drawing depends on its position in the matrix of drawings. The progressing succession of sets of drawings or models, and again, all what I'm saying is relating as much to traditional design media and processes as it relates to contemporary ones, except that in the contemporary world is much more intensified, these issues. So I think that needs to be remembered. That the overall succession is the one that accumulates information in this long-winded process of trial and error that moves through manifold alternatives, which are somehow not, which are dropping away, but they are kind of the decision-making process that discarded all these alternatives is accruing or evolving as something which is so rich and dense of information and intelligence through what it all has left behind. And we always have this kind of horizon of possibility to reflect on, which the medium afford, or the various media afford. On the other hand, we need to see how that whatever we present has carved out from or filtered out from this kind of continuous process of proliferating options and selection and deciding and moving on and opening up a new set of selections on a new plane. So this kind of process is like an evolutionary process of mutation, selection, reproduction. And I want to introduce another concern and aspect. This kind of time structure of the design process has two aspects, and distinguish spacious time, a kind of durée versus point-like time. What I mean by this is the point-like time is that measured with a clock time which continuously and irreversibly time becomes past, where the before and after is made distinct by a decision, by placing a caesura, by moving on to a next step. In a sense, consuming options and fixing a point to then open up a new set of options. Versus that spacious present, so the point-like present is that moment of making a caesura, making a decision, and clocking on and ticking on in time, building up complexity. And the spacious present is also very important, is that prolonged continuance, where this kind of zone of reversibility, where we're kind of lingering, negotiate, and keep options in the mix and keep options open, and that is what the medium also affords in many ways. And what I would argue is that the very introduction of the design medium, the drawing initially, as against a direct engagement with the built environment through self-building, through construction, through building up a construct without the advantage and plane of invention of a prior drawing design process. Compared to that, we have when we introduce drawing for the first time in the Renaissance, we already have that moment of combining design progress with the preservation of reversibility. So the design progress prior to the drawing, of course, the design progress as the construction process and construction progress. And now we can separate out and isolate design progress in advance of construction, and that is relative to, compared to the direct building up of construct in real space as the final product. We have that zone of reversibility of that spacious time. And I think that every single advance in the medium is always about enhancing that ability to combine design progress with the preservation of reversibility. So when we're moving from construction to the domain of drawing, we have that. When we're moving from drawing on paper with ink to a kind of drawing which starting to use tracing paper and transparent layers, we have that ability to kind of work over with tracing sketches and keep kind of shifting and moving and lingering in the domain of options before we finally make a decision and inscribe these kind of browsing explorations into the paper and then move and open up a next step. We move from there into the computational world where the world of design speculation becomes even less material than in the world of paper, more malleable, opens up more spaces of reversibility. And finally, in the parametric model, where we can really build up a lot of detail and precision and progress the design process while maintaining to a large extent this kind of reversibility in the mix. This is where I see a kind of one key kind of aspect of progress in the development of the media. So I want to now set this kind of discussion into the broader terms of my theory of architecture as it is places architecture in the societal context. So first of all, for me, the phenomenon of architecture can be most adequately grasped and analyzed as autopoietic system. That is a self-referentially closed network of communications. That's the discourse, this kind of specialized discourse of architects and designers theorizing and arguing, discussing their work, starting in the Renaissance, in fact, where we have, for the first time, the drawing, as well as the treatise and theoretical discussion published together and circulating in an open discourse. So the architecture as expert communication process, relying on the specialized medium of the drawing and later digital model as its key precondition to allow this discourse to set itself up. Second premise is that society is the totality of all communications, and that within that we have various self-referential closed subsystems of communication, like architecture, but also like the political system, like the economy, like the legal system. That's my kind of understanding of society as a series of co-evolving discourses, each of them taking up particular responsibility. And the responsibility of architecture and design discipline is the kind of innovative structuration of the built environment as one layer through which global societal processes are ordered. So architecture is one of the great autopoietic functions systems of contemporary society in parallel to politics, science, the economy, the legal system, etc. And I'm coming to this point that the special efficacy of each of these function systems relies on a specialized medium of communication, and these have been developed together with and emerged together with these function systems as autonomous discourses. Like the drawing emerges together with the architect as figure, together with a reflective discourse, and together with an understanding of architect as an agent, author, who actively, of course embedded in a discourse, now projects and changes society in its kind of spatial dimension. And I just want to allow for that comparison of the drawing and modeling and architecture with, for instance, the medium of money in the economic system. That's also one very specialized system of communication, which was able to set up and make the economy independent and becomes a kind of automatic, self-referentially closed, specialized system of communication, which takes up a particular responsibility within society, but it is also through that specialized medium setting itself apart and develops its own dynamic. And also the medium of power in the political system could be compared, or the medium of demonstration and empirical demonstration in the sciences. These are parallel processes which set out at the dawn of modernity. And these media are integrally involved in setting up these autocratic subsystems. And this brings me back to this distinction when architecture first emerged as autocratic system of society, and we need to distinguish architecture as innovative designed architecture from mere building, which is tradition-bound building. And we have all prior Renaissance elaboration and build-up of complexity in the built environment is a kind of tradition-bound, semi-unplanned, unconscious, largely incremental evolution along the lines of mutation, selection, reproduction, building up a kind of edifice which proliferates and succeeds. But then we have what I call the Big Bang of architecture for the first time, where this kind of unconscious, cumulative accretion evolutionary process, which took many thousands of years, and to reach a certain point, we have that moment of separating out the architect as with the tool of the drawing to represent and move from the direct engagement with the physical world into that plane of representation, this plane of paper, and suddenly with this kind of dematerialized representational realm can very, very rapidly manipulate, promote, and communicate, and experiment with new possibilities. And at that point, of course, the initial drawings are just representation of what has evolved in the medieval city, becomes the ideal city, but then sets up that kind of rapid, accelerating trajectory of innovation. At the same time, if you innovate and you deviate from what has been done previously, you need to argue for that, you need to convince, and to do that you need theory. At the same time, you have theoretical treatises coming up, a kind of consciousness of innovation like in Alberti, but you also need that success medium. You can only gather support and build up credibility for your unusual and innovative proposals which concern larger stakeholders if you have that medium of representation which can make the not yet, the unseen, the different, perceptually palpable and compelling through representation. And the invention of perspective was critical to that respect as well. Even to know as a designer yourself, what are you proposing, what are you projecting, what are you trying to gather investors, a whole community for years and decades to commit to such a project. You need to have a compelling medium to envisage and project such projects. That's the aspect of the success medium. You can only communicate and will only communicate if you have a chance to be successful. So, and that projects back into the reality very quickly, and then expands rapidly to transform in a few hundred years the physiognomy of this planet globally. So the function of these specialized success media, in very general terms, that covers all of them, also covers money and politics, etc., is to make otherwise highly improbable communications or social interactions probable, indeed a daily occurrence that can be expected. So money makes the improbable probable, namely that we are able to be relaxed, envious onlookers with respect to the consumption and enjoyment of others, without demanding our share whenever we see others eat. We can do this because we have money, the universal equivalent, in our pockets. So money is doing something, offering a totally new dynamic into the social process. And the same, I think, is political power and mechanisms of holding and projecting power. It makes the improbable power probable. Also, for instance, in corporate structures and administrative structures and bureaucracies, namely that we continuously follow both general constraining rules as well as the concrete instructions of our superiors against our natural instinct, desires, and immediate drive for organic comfort. So this kind of long chains of instructions, command, the great integration of many forces in the division of labor needs the specialized medium of power. We need the specialized medium of money, of integrating that and having many manifold and different and individualized desires fulfilled and exchanged wherever we like. And I think the medium of drawing is doing something similar. It is also a kind of success medium. It makes the improbable probable, namely that we're able to convince ourselves as well as clients, stakeholders, and the community at large that they should invest resources now and trust us with the creation of complex, novel, unseen, long-term built environments that will not be available for inspection before it has been constructed a few days down the line. And that is kind of an incredible suspension of disbelief, which we can only engage in on the back of these powerful media of elaboration and communication. So, and in that respect, I think what was clear also in the previous presentation, that this capacity on ever more complex and large and intricate scale with ever more demands onto the built environment needs to be demands that continuous upgrade of this medium also for the purposes of communicative success in this sense. So like money and power in their respective domains, economic exchange and political decision-making and administration, the medium of drawing modeling is universally applicable in its specific domain of operation. So anything and everything could be exchanged for money, anything and everything could be instructed and regulated through political or administrative power, and every and anything could be drawn or designed. That is the universal universality of these media. But I think it's also important that that all of these media need to continuously upgrade in this kind of co-evolving, ever more global and complex and demanding societal life processes. So, and I think this upgrading concerns all these media. So the new forms of money and financial instruments, the kind of electronic money and financial system based on computational processes, not only in terms of credit money and electronic money, but also in terms of calculating the profitability and value of assets. We need computational processes, the same as the new mechanism of social control and administrative power, registrations and statistics, and all the tools and instruments of ordering society through administrative processes and collectively binding decisions, if you like. And the same applies, of course, for the medium of architecture in terms of the tying in and building on the computational capacities and enriching also the models in the way was discussed earlier with engineering constraints and intelligence, and have an ever more sophisticated and light-footed and penetrating and convincing and compelling set of speculations we engage in, and which we've left the kind of hand-elaborated drawing where you break your back for 3 weeks. What you achieve there is so far behind what we actually require and demand of us today. That's my point here. So, how am I doing time-wise? The overtime? Okay. So maybe I leave it here. I mean,